Hi, Jeremy. How are you? It's Kathleen Duffy. I'm here with Demetria. Thank you for joining us at the Radiology Expert Corner.
Hi, Kathleen. Hi, Demetria. It's wonderful to be here and really good to put faces to the names that I have been conversing a lot on email with.
Yes, the feeling is quite mutual. We were hoping to begin today with some questions on, how does a person that grew up in Singapore continued their education or career in Switzerland, and then is now in Abu Dhabi. How did you get involved, or what sparked your interest in bioengineering?
All right, so I started as a mechanical engineer for my love of cycling, I guess. And so from that, I was really interested in the different kinds of materials that went into building bicycle frames. So initially we had aluminiums, we had steel, and then we moved on to titanium and carbon fiber. So I was really interested in materials. And then I went to university, I went to college, and I had a professor, and he was at that point, maybe in 2000 and I guess 2002, where he told me, I was in his class and he said, "Hey, do you want to join me in my new lab? I am using materials to help the medical field." And then I asked him, "What do you mean by helping the medical field?" And then he said, "I'm going to make tissues in the lab so that it can be transplanted into patients." And so that kind of sparked my interest, only because I really wanted to be a practitioner, a physician, but the strict streaming education style of Singapore kind of made that possibility very slim. And so this was another way which I could actually contribute to that profession. And I like materials, so it was a natural fit. I spent 6 months in his lab. He introduced me to the world of degradable polymers, and these are synthetic polymers. Also, that's when, believe it or not, 3D printing was incorporated into building these scaffolds, because in order to build or replace tissues, it has to be in a 3D format and not two-dimensional materials. And so, yeah, so I did my internship with him. I did my, I guess you call it the capstone project or the final year project, and I did pretty well. So I was really interested in this whole bioengineering field, how I can also use computational skills to improve, for example, biomechanics design for the scaffold and for other for the anatomy. So when I graduated, he kind of spoke to me saying, "Hey, the job market isn't that good. You want to stay on for a master's." Being lazy, I said, "Why not? I get paid and I still really enjoy what I'm doing." And so that went on for 2 years. Subsequently, the same story happened. He said the same thing, kind of, not exactly, but I was slightly tired of staying in the same place for a few years already. So that will be about 5 to 6 years already. So I said, "Hey, yeah, I'll be interested to have you as my supervisor, as my PI for my PhD thesis, but I do want a change of environment." So he kind of hooked me up with the guys from medicine. So my PhD is actually from the Faculty of Medicine, but my thesis work is still very much into biomechanics / biomaterials / bioengineering. So there I did a lot of spine biomechanics, computationally, and a little bit of materials. I did bone cement, mechanical characterization, use the parameters obtained from these characterization experiments into computational simulations, so on and so forth. But that was also the period where, his lab's tissue engineering initiative really took off. A lot of my peers were doing tissue engineering, And I'm like, I'm already almost finishing up my PhD, so it's kind of pointless for me to switch. So I was like, all right, if I'm continuing research, I really want to get my hands, I guess, dirty in the tissue engineering or the wet science field.
Yeah.
I finished my PhD from the National University of Singapore, and also concurrently, Singapore was putting a lot of money into biomedical research in terms of the A-star labs. And I joined the Institute of Bioengineering and Nanotechnology. And so there, the director did ask me, what do I want to do? Immediately, I said, tissue engineering, nothing else, nothing computational, nothing to do with bones, something else. So she was kind enough, put me under a group that was doing kidney tissue engineering, where I, again, use biomaterials to be able to support a confluent monolayer of kidney epithelial cells to be placed into a bioreactor, which is supposed to act as a bioartificial kidney that allows dialysis patient to have continuous dialysis on the go. And this continuous dialysis is supposed to be much more beneficial as compared to intermittent dialysis, where they go into a center and get their blood treated for 2-3 hours at a single sitting. But in that project, I did realize that the cells that were in my hands or in the bioreactor kind of behaved differently as I operated that bioreactor at different speeds. Because bioreactor, you have all these fluid flows that goes through. So the cells did sense this fluid flow. And so that really interests me. I mean, interests me in terms of basic science. There was not much opportunity in to study basic science in that institute. And so that's how I looked around, and I was introduced to the Swartz Lab at EPFL at the time. And she was interested in cancer and immune cell bioengineering. And a lot of it has,
this is the one.
This is the one in Lausanne. Right? Yeah. So the PI there was Melody Schwartz. And there, I was introduced into this whole new realm altogether, where things matter at the single cell level. And that is also where I got a better hands or better practical skills in handling softer biomaterials, collagen gels, different kinds of extracellular matrices to basically recreate or biomimic the microenvironment that each cell is supposed to be in. Of course, that includes the flow aspects that I initially kind of tickled my interest into this whole field of mechanobiology as well. I did not spend too long in Lausanne, in EPFL. I think it's about two and a half years. And faculty positions are not easy to come by worldwide. And there was an opportunity in Abu Dhabi where they are starting a new bioengineering division spearheaded by partners from Georgia Tech. And Georgia Tech has a very good BME program, and so that kind of pushed me to apply and join. And I landed up in Abu Dhabi, and that was at Khalifa University, which I spent about 5 to 6 years. That in my time there, that's where I actually did a lot of teaching, and that sharpened my teaching skills. But I really wanted to be very research active, so that I kind of missed that after a while. And so when New York University Abu Dhabi gave me the opportunity, I joined them. And right now, I guess my research is involving a little bit of immune bioengineering, where I recreate the environment for immune cells and study their behavior and how they respond to mechanical stimuli. So that's mechanical stimuli which you purposefully put into the system. But on another research focus, I'm actually studying what happens when we remove this mechanical stimuli, and how do immune cells react to that.
Right.
So you can put that in the context of astronauts and space travel. So that's when there's no more mechanical stimuli because gravitational forces are minimized or in the micro levels. And so whatever we built in the lab to study immune cells, we try to put it onto something called a random positioning machine that spins randomly, recreating this microgravity environment. And that's how we study now cells not exposed to a mechanical stimuli, and determine to see if what actually causes astronauts to have a suppressed immune system while in space. And so that's kind of my two research agenda right now at New York University, Abu Dhabi.
We'll actually get into more specifics into that. Thank you for sharing all of your journey basically to getting here.
So, hi, Jeremy. I will join Kathleen in thanking you for being here with us today. And then I will move to the science block of the interview. And I wanted to start by asking you about your lab. So how and when it has started?
So my present lab at NYU Abu Dhabi started in 2018, January the 2nd. I remember that day very well because no one was at work.
Okay, and how is the structure right now? Do you have postdocs, master, PhD, undergrad?
I have 2 postdocs right now, and I have also 1 PhD student and 2 research assistants. So the format of my team, because I'm in bioengineering, so I have 1 postdoc who's a biochemist by training, but he's the one that is involved in all the rebuilding or reconstruction of the microenvironment for the cells, all the collagen, all the polyacrylamide, and all the ECM components. He's the one that's involved and the expert in it. My other postdoc, she's the aerospace engineer, and she's the one interested in microgravity, and she's really good at building stuff and putting stuff together. And my 2 research assistants, one is a immunologist, so that works out very well for me because she's the go-to person when we have questions about immunology. And the other guy, he's just a maker. Tell him whatever you want, he goes out and tries to make it, and he makes it really well. So I'm very fortunate to have such a capable team. And my PhD student, she just started not too long ago. So she's still trying to find her way in terms of her direction in her thesis.
And you already started mentioning in the beginning about the research lines that you're working on. So the main point, I think it's immunomechanobiology, but can you divide it in another way? How it is the research lines in your group?
Yeah, so we have 2 primary focus, and correct, you're absolutely correct by saying that it's immunomechanobiology, or basically how does mechanics or biomechanics affect the immune cells. So the first one is we recreate either normal tissue or disease-like tissue and see how immune cells respond to it. So a good example will be, for example, your tumor microenvironment. So the tissues there are really stiff, right? But if you take a histological section of a tumor, you'll see there are a ton of immune cells. And most of these immune cells do not work, obviously. If not, the tumor will be eradicated. So our take on that is the tissue mechanics actually plays an important part in modulating the immune cells. There are many other groups that have also embarked in this direction. And our novelty is in studying the way dendritic cells actually get affected, because we feel that the dendritic cells are the important ones because they are the key ones that actually brings the signals to the lymph nodes such that the adaptive immune response can come and do what it's supposed to do. So that's one focus where we play with biomaterials or hydrogels or softer biomaterials and see how they affect the innate immune cells. So the other focus is when there's no mechanics or there's no mechanical forces on these immune cells. So whatever tissue we build, whether is it pathological or healthy, we put it onto a random positioning machine. And then we spin this machine, which, like what its name suggests, it goes in a very random motion. It goes at random speeds. Basically, it cancels out all the forces and reproduces microgravity. And from there, what we hope to study is how does the immune system of astronauts get affected? It sounds straightforward, but when we bought the RPM machine, we realized that our normal experiments in the lab cannot be just transferred and placed on the RPM because it doesn't have such facility. So imagine in the lab, we are using 24 well plates, but on the RPM, we have to use a T25. So that reduces the amount of experimental repeats, technical repeats, and it wastes a lot of expensive reagents. And so a bulk of our work involves engineering. I mean, we are an engineering lab after all. Involves miniaturizing a lot of what we use in a normal cell culture lab on board an RPM, which is about the size of a soccer ball. You call it soccer ball, right? Not a football. Yeah, the size of a soccer ball. So the RPM is the size of a soccer ball. And so we have to miniaturize all our cell culture experiments and try to automate it as much as possible onto this RPM. The automation is important because the RPM takes some time to reach to a steady state level, and it also takes some time for it to come down to a halt. So we are not, right now, no one is sure what's the lag time for mechanical adaptation or readaptation of cells. And so to minimize that, we are trying to look into optimizing or automating a lot of biological experiments on board the RPM.
Okay, so this RPM is to reduce the levels of gravity in the...
That is correct.
Okay. And then, so you do the experiments in these conditions, but also in normal gravity conditions, and you are interested in evaluating the cell behavior under different matrices. This actually, it's something that we already discussed a bit in previous interviews, and also definitely we have some monthly publications that we discuss the importance of analyzing the metrics, stiffness, how it influences cell behavior. But the immune cell behavior, it's something quite novel for us. So could you tell us a bit more about the motivation of the group to study specifically the immune cell behavior on different matrices?
So I guess I used to be a tissue engineer, and I've also have a lot of peers who do stem cell engineering. And I remember my experiments for tissue engineering, it can go on for 3 weeks to a month just for a single sample. Just to see how the cells come together, morph together, and then produce some functional effects, right? And so when I was trained in immune and cancer cells at a single cell level, I thought, hey, it's easy, single cells. You run the experiments for maybe 3-4 days, you get some results. But little did I know these cells, although it's simple to run the experiments, the results that comes out are so multiplex and complex that it makes analyzing the data a little bit more difficult, but also very exciting because it gives us more opportunity to look at data analysis in multiple ways. So
then you were mentioning that normally you create biomimetic models. So then you study the immune cell behavior on them. And I understand the importance of that in a context of basic research, as you also mentioned, to understand what happens in pathological conditions during the course of a specific disease. But do you think also that this kind of research can help the outcomes of tissue engineering?
Yeah, for sure. I mean, if you think about it, there's a lot of groups out there who do like tissue engineering. They also do tissue engineering in what you call organ on chips, right? Meaning they recreate those tissues on microfluidic platforms, or study the drug response to these organs, or study disease. But I think a lot of these single organs chip studies are missing is the immune component. I think it's getting there, but I think what's really important is to have a parallel immune component to these chips, to all studies, because our bodies do not, just, or our organs are not just, they're not single, right? They always have a parallel immune system. And there's so much crosstalk between the immune component and the tissue component. So I think that's lacking, but I've also seen that there's a trend that's increasing. So for a good example is like a lot of people are trying to build a tumor microenvironment. And now they realize that it cannot exist alone, those kind of studies. So now there's a lot of groups also embarking on the oncoimmune microenvironment using microfluidics.
Okay, and what do you see as main challenges when studying the mechanobiology of immune cells?
One of the main challenges is, we use collagen predominantly, and we would like very, very much to be able to recreate the microtopology of cells, the tissues of humans, right? It is, of course, we can do that, get some biopsies and compare porosity, etc., but I do not think we are at a comparable level yet. I think that's the main challenge. Right now, we are just changing one, what you call this microarchitectural parameter at a time, just to see the difference. But then in a tissue, the microarchitecture is also dynamic. So it'll be nice to have systems that are also dynamic at the same time.
And how do you process the collagen? You use 3D printing, or you just use casting for creating these models?
So right now we're using casting, but ultimately, we can cast 24 well plates, no problem. They're quite perfect actually. But we want to do high throughput testing, which a lot of pharmaceutical companies are interested in. Definitely, we need to try to be able to dispense them, and to dispense them in an automated manner, such that user variability does not come into play anymore. Of course, in terms of tissue engineering per se, it would be nice to be able to create 3D structures with these collagens without additives. So now there's a lot of additives that initiates or makes the cross-linking of these polymers very rapid. But of course, these also changes the microtopology. We have not had a chance to, in my lab, we have not had a chance to study how the immune cells actually respond to these fast polymerizing collagen just yet. But we recognize that that's important. It's also a challenge because in order to build 3D structures just out of collagen, you need this quick polymerization.
Mm-hmm. And you mentioned we are talking about collagen, but do you also use other biomaterials in your lab?
Yeah, we use polyacrylamide. We also use agarose. We use hyaluronic acid, but these are used less, especially if, because there's a lot of things we want to decouple sometimes. And so collagen might not be the best substrate. And so a more inert substrate might be better, such that we can, for example, I mean, if you talk about microtopology, we can actually use polyacrylamide with patterning and see how cells actually behave to different geometrical structures.
And so in the context of mechanobiology, the mechanical characterization is definitely something that I believe it's important. Yeah. And we know that this can be challenging for soft samples with cells. So can you share with us the main challenges you had or you have for characterizing the mechanical properties of these matrices, these models?
So there's a lot of school of thoughts on this, right? I mean, a lot of people use AFM, and also a lot of people use rheology. And so in order for us to assess mechanical properties of hydrogels with cells embedded in them, we use Rheolution's non-contact and non-destructive kind of testing. And so having said that, we can actually put a sample, for example, in our recent study, we put a sample with fibroblasts exposed to immune cells. And so the immune cells kind of crosstalk and orchestrate the function of these fibroblasts, whether they want to do matrix remodeling or not. And because that's a remodeling of the matrix, as an engineer, one can imagine that because the microstructure is being rearranged, the macro mechanical properties will have some changes. So that would have not been possible with destructive testing. So with the elastosense from Rheolution, we managed to be able to test and get results based on what these tiny cells within matrices are doing. And so that's pretty exciting for us.
That is very interesting. And have you ever used other mechanical testers as well in your context?
Not with cells. I've used before AFM. I've used before, conventional rheology, but definitely not with cells. I mean, with AFM, sometimes when you're pressing, the question is, what are you pressing on, right? Are you pressing on the matrix or are you pressing on the cells? Yes, you can do imaging, but if you have a hydrogel, a three-dimensional hydrogel with cells, the results are again pretty questionable. For destructive testing, that doesn't really work for us because that will mean multiple samples, a lot of wastage. Whereas if it's non-destructive, you can use the same sample over and over again, and this does not. So whatever variability you know is from the cellular function itself and nothing else.
Mm-hmm. So you do mechanical characterization over time of your samples to see how it evolves over time?
That's correct. That's what we do.
I heard that your mechanical engineering, your love for bikes, it actually brought on something beyond just liking bikes. I hear that you do triathlons. Tell me a little bit more about that. How did you get
involved? How did I get on in that? So when I was doing my master's, somehow I'm not sure if, so I had hyperthyroid disease where my heart rate was really fast. And so I was on medication, and in order to control my heart rate a little bit more, what I heard was to do endurance sports. And so I mean, as a kid, I loved swimming. And of course, like what you mentioned, I like cycling a lot. And so it's like a natural progression by putting both of them together and then do the running bit. So triathlon was something I took on quite seamlessly. And I've been doing it ever since. It gives me discipline. It gives me a structure. And it also gives me a place where I can not entirely forget about research, but gives me a space to step back and actually think about how I want to fit all this data that we are acquiring as a jigsaw puzzle. So I mean, if you're swimming laps in the pool, it is one of the most boring things ever. So I do have an automatic counter on my watch, so I just keep going, to and fro. But at the same time, I'm like, okay, we have this data ABC that we acquired, and what does it say to the whole picture of the research that we're trying to achieve?
Gives you time to
it
think.
also, it gives me a quiet space to think while I'm still working out. I know it doesn't sound too possible, but there is some possibility.
Yeah, there's a lot of people that use sport as their outlet in being able to process information and being able to. We need to pause actually for a lot of our ability to problem solve and connect. Tell me a little bit more of what is a day in a life of Jeremy Theo when it comes to your typical day. How do you start your day?
So I start my day really early. Like I mentioned before, I do endurance sports, triathlon. So I have to start it early, get the training out of the way and not interfere with family life. So I'm up like 5 a.m. I go for a run or bike. And then I'm back. I have 2 kids, so I send them off to school. And then subsequently, I just head straight to the lab. First thing I do, I grab a cup of coffee with the team. The way I build the team is it's pretty easygoing. Recently I heard another student says that actually mentioned that my lab is homely, and that's how I like it to be. Where yes, we all have different roles in that hierarchy, but the lines are really blurred actually. Like if I have the time, I know my lab members hate this, but if I have the time, I'll actually still conduct experiments, and they probably hate it because they will have to be the ones finishing up, because things will start piling up on my plate, and I promise them that this year I will not start anything on my own. But
hands
other
off.
than that, hands off. Other than the morning coffee, and then I go about to do my own stuff. But as much as I can, if teaching scheduling does not interfere, we'll have lunch together. And that's when we are all passionate scientists. That's when problems in the lab or exciting things in the lab will be filtered and come up in the conversations. And so there's a lot of labs that hold very formal meetings, very scheduled, but by interacting with the lab on a daily basis, I don't see the need for that often. So that reduces, I guess, kind of the stress on the lab members, where they don't have to prepare formal presentations, etc., etc. They only do it as and when required for, when something is formal. Other than that, so after lunch, we go about our own, whatever we need to do. For me, I come back, make sure I spend some time at home, and before I open up my laptop again. And then the day it just cycles. I mean, it doesn't seem mundane. It doesn't seem a chore to open up my laptop after work, because I think I've heard this before. Research is not a job. It's more of a lifestyle. And if you listen to the conversations we have, it always goes back to research, and that keeps me excited. It keeps the lab members excited. So I don't think I'll change that style of management.
Based on that, given my business background, I have to say, when I look at PIs, I see an entrepreneur. I see someone that's looking for funding. I see someone that looks for opportunity. I see someone, that is always striving to push their team forward. So I often relate those two worlds as very similar. I see a lot of traits of PIs with entrepreneurs. So I could see how this is part of lifestyle, because that's exactly how it is for entrepreneurs. In that vein, what would you give your younger self as advice in this field?
if I have to turn back the clock, I wish I could, but that's not possible. I will definitely be more active searching for opportunities. Like what I mentioned to you before, how my progression and made me end up in Abu Dhabi was, you know, my professor said, why don't you just stay on? You're pretty good at what you're doing. Just stay on since the job market is bad. And I also specifically said I was lazy, and I said, okay, let's do it. But if I could turn back the clock, I mean, I would have tried to see what opportunities are there out, you know, beyond Singapore. I mean, being where I am now, I see things, you know, occasionally I see things coming back full circle. So I have no regrets on taking the back seat on that. But if I had to change one thing in terms of research or career, that's one thing I'll do. I'll seek out more opportunities, and I will put myself out there more to people I meet at conferences or invited speakers. That's something I notice graduate students or, you know, postdocs don't do enough. They feel like their work is, it's all that matters. Yes, it matters, but also, you know, what matters is putting your name out there, not just for, you know, getting reviewers and what have you, but also, I mean, the scientific community in the end is quite small. You always would like to have coffee or drink with a friendly face. And so, you know, right now, if I go to Canada, I can go to Revolution and see the both of you.
100%. You are totally welcome, and we look forward to it. You might not want to come during the winter, but
no.
So thanks for sharing that. On a side note, I do not think you're lazy. Quite the contrary. I understand that, you know, hindsight is 2020, right? But that is not the first thing that comes to mind when I look at your career. So it's interesting to get your personal perspective, and I think your advice is really great in that you know, students might be shy in, you know, what shall I do next, that kind of thing. So I think you know, your advice is going to be well received from the students. So what would you suggest for students listening to this interview who are starting in this biomedical field? What would you suggest to them?
Well, let's see. I think one key thing I would suggest is seek out clinicians. I think that's missing. That's a big part missing. Don't just be bogged down by the basic science that you're supposed to do. Seek out clinicians, find out what are the needs, what are the wants, and then you will have a bigger impact. Bioengineering or biomedical engineering will then have a bigger impact towards the medical profession. Because if you don't talk to clinicians, you don't talk to people who are at the front lines of medicine, you don't really know what's needed. And I feel that if you can build projects around what's needed, the amount of funding, I guess, the amount of support you get will definitely be far greater than what you will be involved in.
As a leader, you know, how do you go about motivating your group? What's your special sauce in keeping people motivated?
Surprisingly, I think I made good hires. They are the ones that are motivating me, and I'm very lucky. I actually learn from them as well, and I'm just managing them. But there's no secret sauce to it. I guess the secret sauce was to make sure that everyone just clicks. One of the big things that I do, I don't just hire based on CVs. You know, CVs are pretty much on the same levels throughout. I think the key thing is to ask present team members, like, Is this someone you will go have coffee or have lunch with on a social basis and not just at work? So that has been my mantra, I guess, in terms of hiring. And I don't think that will change. It's worked out well.
When recruiting new employees, when collaborating with the PIs, what are some of the most important qualities that you seek?
When collaborating, I think there must be full transparency. I've seen a lot of collaboration fails and what do you call this, workplace relationship fail just because collaboration was not done right. Ideas can flow, but I think one of the main things that needs to be ironed out from the very beginning, it's all about publications or grant writing or patents after all. Set it out straight. Who are the lead authors, the senior authors, that stuff which a lot of people don't want to talk about, but I feel like it's important to set it straight. If it's set straight, then at least the expectations at the end of the project becomes less, and there will not be sourness in the relationship. So I think what I look out for is for people who can bring to the table skill sets that we are missing. It might not be a 50-50 thing. By all means, I mean, we are all here to collaborate and bring science to greater heights, right? And not incremental heights, just greater heights. And yeah, so we don't always have to fight for the glory, basically. But I mean, personally, I'm not a person that is a glory hunter, but I'm just, happy with the work I put in, and that's sufficient enough for me.
So I wanted to look at the future, vision of what the future may hold. So what are some of the emerging challenges and trends in the biomedical, bioengineering fields, when it comes to building these materials? What kind of aspirations do you have for this?
That's a really tough question. What's the future? Of course, I mean, it's a idealistic future where, we don't need organ donors anymore. Be able to print organs as and when we like, and to replace organs. But I think in order for us to do that, we need to sit down and talk a lot more in terms of the different labs, the different groups, including clinicians, sit down and just really trash it out. I feel like there's a lot of overlap. And if we are a little bit more transparent, overall, we can achieve more with a combined pool of funding, right? And I think that goes back to just the way the scientific community is. Everyone is struggling, fighting for grants and stuff like that. But I've seen research societies where there's not much fighting going on, and I feel like the impact of their science are far greater than in societies that you have a lot of interfighting for the crumbs on the table, basically. So I hope, like, future everything can be open,
more collaborative.
More collaborative. I mean, right now with I'm talking to you, I'm in Abu Dhabi, you're in Canada. It's possible. It's just that we're not doing enough of it.
I could totally see that. And I think that, the pandemic has ironically opened new venues of communication that we've become much more comfortable with. Right now, it's much easier to reach out to someone and actually see them face to face, where sometimes, you'd be talking on the phone, you'd be exchanging emails, but there was no face to face, right? I think that the face to face is happening a lot faster than we were accustomed to, probably before, COVID. I mean, to a certain extent. So, so when you talk about your vision, what do you envision like in the next 5 to 10 years, concretely when it comes to bioengineering? Like what do you expect? Where do you think we're going with this?
Concretely, something that's possible, I guess. I mean, what I'm gathering, because I watch TED Talks, there's a lot of, organs that are being implanted already, clinical trials, and things like that. So that's super exciting. All we need to do is just to improve them to a state that it's becomes more widespread, more available, and hopefully there's no, what do you call this, disparity on who can actually receive these organs.
If you had a magic wand, Jeremy, what would you wish for in this field?
What would I wish for in this field? Unfortunately, it will mean that this field will not exist. It means everyone leads a healthy lifestyle, healthy for a good and long time, where none of these medical intervention or bioengineering intervention actually is needed, right?
And that's your magic wand.
that is my wish, fortunately or unfortunately.
And if you had a magic wand specifically in this field, what would you use it for?
So if I had the magic wand, I wish all protocols that we read on papers are reproducible. I think that's one of the things or hurdles that the scientific community or the bioengineering community is facing with. I mean, people, I guess, because they are doing a certain protocol over and over again, they think it's straightforward. But if we are, again, more transparent with stuff, maybe scientific progress will grow much faster. So I wish, if I had a magic wand, I wish all protocols to be reproducible before they get published.
We've had a number of people that actually talked about one of the visions or hopes in the future was to collaborate more with clinicians. How do you see that happening? Considering, it seems to be working in parallel worlds. How do you see that possible in this field, to be able to work on, like, I guess, removing some of the obstacles, or how do you see that as being a possibility in the near future, and being able to collaborate more with these clinicians?
I think for clinicians, they always have an investigative mind. They always have a inquisitive mind on how to improve their practice, right? I think the hurdle for them to actually participate very actively in research will be their administration. So my PhD was in the medical faculty, and my PI was a consultant in the hospital. Even so, he was my direct PI. The time I got with him was very minimal. I mean, as a hospital administrator, at the end of the day, it's the patient's FaceTime of the doctors with the patient, and patient first, research is second. So there are some institutes that link up very nicely. For example, I guess Georgia Tech has Emory, and other cases like this, where it's a partnership with a university or maybe a teaching hospital, where research is a component of the education. That has shown good success as well. There are also research societies where medical doctors will have to do 1 year research before going out to practice. I think this is more in Europe. I'm not sure about Canada. Sorry.
Yeah, we have that in Canada too.
Okay, that's really good.
Yeah.
So, I mean, if the clinician is like, hey, I like research, and maybe not so much FaceTime with patients who can be painful, And so I dedicate, a bulk of my time, or try to find ways to get involved in research. And that's a way to go around that. Yeah, so it's building, it's like what I like to call it, is building a very conducive ecosystem. That's important.
Yeah.
Where the clinician is not accountable if he takes time off to do research. You need a conducive environment. Everyone talking the same talk, walking the same walk. Then you'll have a much better ability to translate basic science into the clinics.
So now the challenge will just be to implement this.
So one thing that I was thinking during this time, it was more a little bit related to the beginning of my questions. Because, for example, yesterday I went to the internet to read a bit more about mechanobiology of immune cells. And I couldn't find actually much work that was not related to your lab.
Oh, to my lab. Oh no.
Yeah. So I wanted to ask you if this perception of mine is also yours. Like, do you see that there are not a lot of people studying this?
Oh, what you're saying is there's not a lot of people in the field of immunomechanobiology.
Exactly. Yeah.
So maybe your search term was a little bit too specific. So if you search immune cell mechanobiology, I'm gathering that you'll find a little bit more, but also not so widespread.
Yeah.
There are people who do it, but you are absolutely correct. Not many groups are doing it.
And I imagine that this is a big challenge for you also, because when we have people working, it's easier to reference ourselves, to see what we are doing different, how we can improve. But if we don't have a lot of work, I imagine that this can be challenging for your group as well.
It is very challenging because the results we get, we can't, like what you say, we can't reference to see if we're on the right track or not. And so we have to be extra careful of the results that we put out, so as not to shoot ourselves in the foot, when the time comes, or hopefully the time doesn't come. But yeah, we try to analyze things over and over again, using different ways of measurements, make sure they're telling the same story. That's what I meant by piecing together the different data that we get, because in this day and age, you can get a lot of readings just from a single experiment, and sometimes they don't cooperate. They tell you different things, and so we make sure that we argue our findings well, to make sure, since we don't have a point of reference, we make sure that our arguments are sound and concrete.
And in your experiments, normally to analyze cell behavior, you analyze markers apart from the mechanical properties? Yeah,
so we like to do a few things. We like to do it, I call it multi-resolution testing. So we are fortunate in New York University, Abu Dhabi, to have a very good sequencing core. So I am not a genomics person, but my researchers would like to enhance their skill sets and learn about it. I say, by all means, go for it. So we study our cells at the gene level, marker level, secreted protein level, and then functional level. So if our paper in regenerative medicine, that's functional, where it's actually controlling another cell type, right? So we, not only that, in the functional level, we make sure that they can do what immune cells are supposed to do, including migration, including its ability to uptake antigens, its ability to trigger adaptive immune response. So this is what we classify as functional. Again, it might be at a gene level, but not at the functional level. And then, so that creates a whole lot of problems. It's nice to study everything multi-resolution because it creates a thorough story, but not all the time the story is very smooth flowing.
You're working, your work entails working in understanding astronauts. Why have you chosen that group of individuals? Is it the environment that they're in that is so different than ours? Or because we often study the elites because it sort of trickles down to the rest of us, or how?
That's an interesting question. So the basic truth is my postdoc, the aerospace engineer, she's involved in a lot of European Space Agency projects before I hired her. And she's the one that pushed this agenda. Initially, I was like, you know, astronauts, we're only serving the purpose of a 0.00, I don't know, 0.001% of the population. What has that got to do with us? But if you read on further, there's actually a lot of things that we can learn from astronauts or experiments in microgravity conditions, things that we can translate back to Earth. For example, an example is in that kind of environment, there's a lot of what do you call this, physiological outcomes that mimic people who are aging and people who have chronic metabolic disease.
Right.
So it's a very good environment to study all that before a person actually ages, right? I mean, when a person ages and you want to extract cells from this person or to study this person, they won't sign off on it.
Right.
So it's an environment that we can study all this and see if there's anything that we can do to help to benefit health on Earth, basically. And so I don't study astronauts per se. The hope is, you know, one day we get to send our experiments to space for real microgravity. But right now we're doing everything on Earth, on ground, and hopefully that gives us the initial data to write for a grant to send experiments to space. Thank you for your time. It was good to meet the both of you, and thank you again for this opportunity. Looking forward to your next email.
Indeed. Yes, hopefully it won't end up in spam.
All right.
All right. Take care. Thank you.
Thank
Good night.
you.
Bye.
Bye. Good night.